Okay, let's start. This is 20. So let's do a quick recap. So in the last few classes, we have been looking at the idea of reciprocity and inter-reciprocity in linear networks. So first, we saw that if you have an LTI network having R, L, C and control sources, say I apply a voltage V1 and measure a voltage V2, I could form the adjoint network, and of course you know the rules for forming the adjoint network. So here I will have to inject a current, say I2 hat, and measure the current I1 hat. And what is the relation between these voltages and currents? V2 in time frequency domain, right? So V2 of f by V1 of f was equal to I1 hat. Okay, I1 hat is the output current. Right. Okay. So this just means that the transfer function from the input to the output here is equal to the transfer function in this adjoint network, right? So this is what we got. And of course in time domain even the impulse response was equal, right? And we derived this result using Teligent's theorem, right? And the Teligent's theorem, mind you, comes in the product form. So for this, what will be the result in product form? Reciprocity result. Sorry. Yeah, but I mean in product form, how does it come about? I mean you understand, right? Teligent's theorem we have in the product form, summation of voltage times. Yeah. So if you do that, and finally what result you get for reciprocity? I mean here I have it in the ratioed form, right? So what do you have? It's LTI network. V2 of f times I2 hat of f was, so that I'm just, I mean this is the result you actually get when you apply Teligent's theorem, right? And from this you interchange terms and make it in the ratioed form. Cool. Okay. So this is with respect to LTI network. So we also did this with LPTV. So here we had RLC and periodically varying conductance or gain. So here again you form the adjoint network. So here what is the relation you get in the product form? How did we apply Teligent's theorem here?
At two different times.
Yeah, but for the LPTV network, what did we do? Yeah, we basically did everything in vectors, right? Here you have a V2 of f, but for the LPTV case, it is no longer a constant. So this was basically V2 transpose I2 hat was V1 transpose I2 hat. So, and what was the relation for the harmonic transfer functions we got? Does anyone remember? Or let us say I apply a frequency of the form f plus k fs here. I observe the response here. What should be the input frequency? F. And I should observe what comes at f plus k fs. So what is this transfer function here?
H minus k f plus k fs.
F plus k fs. And this is equal to h hat of k of f. Fine, great. And we also saw the corresponding result with respect to the impulse response. And say for the original LPTV network, the impulse response was h of t comma tau. What was this here? Does anyone remember? Or let's say here in the original network, I launch an impulse at a time ti.
Minus of t minus tau minus 2.
Yeah, okay, let me finish this. I observe it at t0. So when should I apply the impulse in the adjoint network? And observe it at? Okay, so now try to tell me what should come here. Here, at what time I am observing the output? T. What time I am injecting the impulse? So here, what time I should observe the minus of the time at which we have applied the impulse here, which is okay. And the second argument is tau. Is that fine? So basically, these are the results for reciprocity we derived for linear networks, and this is pretty useful because here, if we were to calculate this transfer function for multiple values of k, you will have to do multiple experiments, and in each experiment you will have to apply a tone at f plus kfs and observe what comes at f. But here you just need to do one experiment, apply a tone at f, and see what are the frequency components you get. Right? So let's try some examples. So let's say I consider this LPTV network. See, this is phi 1, and phi 2. So what does this do? It was the single path for the band pass filter, right? So let us say here I am interested in finding h minus k of kfs. Okay. So what is the input frequency? K times fs. And what is the output frequency? DC, right? So let's say I want to find it for say two different values k, 0 and 1. So before you know reciprocity, that is pre-inter-reciprocity era, how would you have done this? We have done this in class, right? Why don't you tell me what the values are? h0 of 0. I mean, why don't you compute now? Don't look at the values. I mean, you have done several calculations like this, right? Yeah, okay. What about this? Why don't you calculate? Okay, I mean, I think you should try to work out again, and I mean, the result is actually j by pi. Okay? And of course, if you want to do for other values, you will have to again apply sinusoid at that frequency and compute. So now we have a new weapon. So let's use it. So how can I find it efficiently now? I mean, I want to find all these transfer functions. One day is like how you guys did it, right? So apply each frequency and find what is the average output. So after what we have learned in the last few classes, can you think of some efficient way to do this? Apply? Yeah, okay. So what should be the network? I should not use the same network. Yeah, I should form the first. This is the original network. So the first thing is I should form the adjoint network. Right? So what happens to the voltage source here? That's short. We are no longer interested in this voltage. So the switch here, what happens? Yeah, it should be phi 1 of minus t, and in this case it is phi 2. Okay, so this is the phase swap. This is 2, 2, 1. What should be the input I apply?
Current.
A current at the output side. So that this is the current. What should I measure? Current through resistor. Fine. Okay, so in the original network I wanted h minus k of kfs. This is equal to what? H at k of 0. So there I applied multiple frequencies. So what I got at DC. Here I will apply the DC current directly and see what are the frequency components I get in this current. Okay. So let's say this is phi 1. Okay. So phi 2 is basically flipped version. So what happens when phi 1 is on? All the current flows here. What is the output current? 0, right? And when phi 1 is off, so you have this connection. So basically you have a 1 amp DC current passing through a parallel combination of R and C. So what happens to the voltage, capacitor voltage in steady state? Basically it becomes constant, and that constant is I times R. Okay. So if in steady state the capacitor voltage is I times R, what is the current? 1 amps here. Okay. So here during phi 2, what happens to the output current then? It becomes 1, and in phi 1, 0. Okay. So the output, this is the output current. This is basically a periodic square wave. And let's say if I want to find hk hat of 0, sorry, h 0 hat of 0, what is it? That's basically the DC of this, that was half. So now h1 hat of 0 is what? I mean, you work it out, it will be j by pi actually. Okay, for normally it is 1 by j pi, for this square wave it is 1 by j pi. This is delayed by 180 degrees. So we'll have a minus sign here, and that becomes j by pi. So this becomes j by pi. So what can you say about h2 hat of 0? And h3 hat is?
J by 3
It becomes j by 3. Right? So now you see that in one shot, you can actually get all the transfer functions. Is that fine? So let me do another example. So let's look at chopping. So in chopping, we multiply the incoming signal by a periodic square wave that goes from -1 to 1, and that was given to the amplifier, and let's say the amplifier has some flicker noise or offset, and let's say the transfer function is the of this. Okay. And at the output you again multiply with the same P of t. Here. Okay. So here, of course, you see that we have basically two contributors to the output. So let's see what all frequencies will contribute to DC at the output from both input and from this noise. Okay, and of course normally if you have to do, you will apply each frequency and see what you get at DC. But now what can you do? Yeah, first step, what should I do first? I should form the adjoint network. Okay, and I mean this is in the form of a signal flow graph partially, so let's use our understanding from last class and make it. Okay, copy paste this. So what happens? I'll basically apply the input this side. So signal directions all change. So this is like a multiplier which imparts time varying gain. So this becomes P of minus t, and the signal flow also changes. Right? You can think of this as a voltage controlled voltage source with this gain. Now it becomes a current controlled current source with everything flipped. Right? So earlier in this network, this was the sensing input and this was the output. So now the control source will sense this signal and push out something here. Okay, so the direction of the arrows change. Okay, so this gain is P of minus t. So what happens to this guy? It's a CCCS, again the direction will flip. Okay. And the nice thing about signal flow graphs is you don't have to worry about what is the electrical signal that you are interested in. It's a generic. So this is A of S, and here you have a summer. It becomes a kickoff point. So if you recollect, if you had a case like this becomes a summer and vice versa. Okay, so here I have the summer, so this becomes a pick-off point. So signal goes here and you feed some output here and some goes here. I mean the same signal actually is tapped in both these branches. Okay, and finally again you have one more thing here, so this will again change. This is P of minus T, and of course here you are no longer applying the input here, this is the output. Okay, so I should apply the input excitation here, and remember we were interested in finding how both Vin and Vn they contribute to the output. So what are the outputs I should look in the adjoint network? Basically the signal that comes out here and what comes out here. Okay, and I was interested in finding what comes at DC, right, in the output. So what should be the excitation? It should be a whatever 1 volt or 1 amp DC. It's just a DC. Okay, 1. So let me take it to the next page. Okay, great. So I apply 1 volt signal here, or 1 DC. So that's getting multiplied by P of minus T, and let's say P of minus T is this. Okay, minus 1 to plus 1. Right. So and let us say the amplifier we approximate by the first order polynomial. So how does the output look like? Let me mark it with green. How will this signal look like? Output of the amplifier. I mean, if it was just A0, what will happen? This input is just scaled by A0, but now this no longer can rise instantly because it has a finite bandwidth. So it will basically rise. Yeah, so it will exponentially rise and fall like this. So this value is A0 and this is minus A0. So what about the signal that comes here? I mean this signal is basically tapped here and the same signal flows here, right? And this gets multiplied by this square wave. So what happens? Whatever was in the negative side, that gets flipped. Okay, so I'll have to probably take it to the next page. I'll have something like this, right? We saw that earlier also. Okay. So this is the current that actually flows into the input side. That is the place where we applied the input in the original network. Okay, and this is the waveform you get. The green one is at the noise side. Okay, and tell me what is this time period? This is half the clock period. Okay, so from this it is clear that what all frequencies from the input can alias to DC at the output? 0, 2fs, 4fs and so on. Right? And whereas from here, for the noise, what is the period? TS. I mean, yeah, period is TS. So what frequencies can fold back to DC? Only 0 fs, sorry, not 0, because this has 0 DC, right? So you will have only fs. Okay, and of course, I mean this You can clearly see from this, else from the norm, if you look at this block, it's not very intuitive that signals around 2fs will fold to DC, whereas signals at fs doesn't fold to DC. I mean, at least from the look of it, you see that everything is getting multiplied by signals periodic at fs. So it's at least in the first look, it might not be intuitive that signals around fs is not folding to DC, right? But of course, when you use the adjoint, it actually follows organically. Okay, and of course, if you want to find what is the strength of each of these components that will fold back to DC, that also we can do. So let me do it quickly. Okay, so and tell me what are these values. This is what the maximum values. This is minus A0. So I can basically split it. This is similar to what we did earlier also. So this I'll split it as DC signal A0 plus something, and what should that something look like? It will look like an exponential, decaying exponential, jumping to minus 2A0. Okay, and you will have this. Everything should be identical. I mean, it's not a great artist. Fine. And what is the equation governing this exponential fall? What I mean, if I were to, let's say this is t equal to 0, I mean, I can define anything, right? So what is the equation? Minus 2a0 e power minus t by 2, right? That's all. Cool. So now, of course, this has only DC, and this has all DC, 2fs and so on. Remember, this period is Ts by 2. Okay. So if I were to approximate this, how can I approximate this waveform? That is, let's say assume that tau is very small, this exponential decays quickly.
1 minus t over tau.
No, I mean in terms of waveform. I mean, see, now the point is I have to find what are the strengths of these frequencies, right? So to first order, I want to approximate to some simple waveform so that I can basically find the frequency components quickly. I mean, it's an impulse, right? It's very small. Assume tau is very small. You're just going to do this. Okay. So basically, you can approximate this by an impulse. And what should be the area of the impulse? That should be the area of this waveform. What is the area of this graph? Minus 2a0 tau. Okay, so this is minus 2a0 times tau. So we'll have this at 0 Ts by 2 also. Okay. So what is the, I mean, if we have an impulse time like this, what are the Fourier coefficients for it? 1 by Ts times the strength of the area of the impulse, which is, sorry, it's here, what is the time period? Ts by 2. Okay. To 2a0 tau, right? This Ck for all frequencies, right? So if I were to find h0 hat of 0, that is basically the DC term in this waveform. The DC term of this is basically sum of the DC here. What is that? A0, and then this is A0, okay? Yeah, minus 4A0. Okay. So what happened? What about h1 hat of 0? No, H1 is when you apply a tone at Fs and you see what comes at DC. What is that? Do you have anything that can alias from Fs to DC? I mean, this waveform is periodical Ts by 2. Only frequency components are 0, 2Fs, 4Fs and so on. So this is 0 and H2 hat of 0 is, it is the strength of the exponential at 2 times Fs. This is just DC, there is nothing. And here what is the, sorry, this
minus 4 A naught tau by T.
yeah, minus 4 A naught tau by Ts. And I mean, with our approximation, all the even harmonics will have the same strength. Okay, but of course you can also find it exactly. So let me quickly show how you might do that also. So now we had just approximated this waveform as an impulse and calculated the Fourier coefficients. And of course that will be valid for low frequencies where you are only interested in the average, but at high frequencies the approximation will not work. So let's say this waveform, one period of it, I'll draw it here. So it's looking like this. And this is minus 2A naught T power minus T by tau. So what is the Fourier transform of this? I mean, minus 2A naught is a scaling factor.
G omega plus
1 by?
G omega plus T.
Ah,
J omega
1 by tau.
plus J.
1 by tau plus J 2 pi F. Okay, fine. And e power minus AT is, U of T is what? 1 by A plus J 2 pi F. Okay, so now we have the Fourier transform of one portion. Now we have a periodic repetition of this signal. So what can you say about the Fourier series coefficients?
Summation of that.
Summation of this. No, this is time domain. Remember this, let's say I call it not P of T, say some X of T.
Sampling in the phase.
Why do you say that?
Near periodic time domain that would be a symbol.
Exactly, right? See, of course you can use your results from what you learn, but quickly from intuitively, you know that if you take a signal in time domain, you sample it. What happens to the spectrum in the frequency domain?
Periodic.
You will have multiple copies of the spectrum like this. Okay? So, I mean, the takeaway is sampling in one domain will result in periodic copies in the other domain. So, here you have periodic copies in time domain. So, which means in frequency domain, it's as though the spectrum is being sampled. Is that fine? So, as he pointed out, it turns out the Fourier series coefficients, if I call this as x of f, that is x of sampled version of f, but what frequency should I sample it at? No, what is the frequency? K times 2fs, right? The fundamental frequency is 2fs. So this is basically K times 2fs. But of course there is one scaling factor here because, I mean, if you write x of f, that is basically integral x of t, this. But if I write the expression for the Fourier series coefficient, how do I find the Fourier series coefficient? I mean, let's say you have some signal, you want to find the Fourier series coefficient. What is the expression? 1 by Ts summation x of t 2 pi some f times t. So you can see that, I mean, there is one scaling factor missing, so you will have to add the scaling here. So, is that okay? That's all. I mean, just intuitively you can just say it, and of course once you have it, let me copy everything. So now I know the exact Fourier series coefficients. So this is what? 2 by Ts times minus 2A naught 1 by tau j 2 pi K times 2Fs. Fine? So this simplifies to what? Minus 4A naught tau by Ts plus j 4 pi Kfs tau. Okay. So now from this, what is C0? Minus 4A naught tau by Ts. So even your H naught hat of 0, you already had a DC term A naught minus this fellow. Similarly, if you do C1, or in the sense the strength at 2fs, I want to find the strength at 2fs, so this is h2 hat of 0. What do you get? I should put what value of k here? No, I mean I already took. Here there's a slight abuse of notations, but I mean here I already put fs 2fs, right? So I'll put k is 1, so what do I get? J4 pi fs tau. Okay, so this is the exact expressions. I mean for other also you can calculate, right? And I mean with our impulse approximation, everything was equal to this guy. Okay, and here you can see, I mean if the tau is very small, for any value of k, you know, you can ignore this and it approximates to this. Fine, cool. So that is regarding reciprocity. So next let's move to something else. So till now we have been looking at LPTV networks, where you apply some input and you measure the output, and till now we have been interested in looking at the continuous time output signal, that is I observe V2 for all time periods, right? That's what we have been doing so far. But it turns out in many applications you might not be interested in the continuous time signal, but samples of this, okay, and the sampling frequency, what do you think it should be? Yeah, in many cases it turns out you are interested in taking the samples of this output, where the sampling rate is equal to the frequency at which the network is also periodically varying. Okay, so this is now some V2 of LTS. Okay, so I mean, someone remember any application where you have seen this? Yeah, basically any ADC or any sampling network, right? So if you want to sample a signal, you basically do this, right? So this is a track and hold, where if your input is doing this, when the switch is closed, the capacitor voltage will track. Switch is open, the capacitor will hold, and it will keep going. And in this circuit, you are not interested in this portion. You are only interested in what is the voltage at the end of the track phase. Okay, so you can take the sample anywhere here. And not just this, if you have switch capacitor circuits where you are interested not in the continuous time signal, but only at the samples. So let's see what happens to LPTV network with sampled outputs. Okay. So to understand it, I mean first let's decompose this LPTV network to something more easy to analyze, and for that we'll take Zade expansion, because there everything is converted to LTI networks and multiplication, which is something we are all familiar with. So Zade expansion, I take the input signal and pass it through a bank of LTI filters and multiply. What should this multiplication factor be? 2 pi k0 FST. So it's not of f. H k0 of f. And everything is summed up. Okay, so let's say this is x of t, this is y of t, but now we are only interested in looking at the samples of the output signal y of t. Okay, so let me remind you, this is the output. Right? So what can we do to simplify this? Let me copy paste. Can you suggest me some way in which I can simplify this block diagram? I mean, till here you can't simplify, right? That is a network. I've added a sampler here. So here you see that I take multiple signals, sum them up and sample it. So I can basically push the sampler here, right? Whether I sum it and sample or sample the signals first and then sum the samples, both are virtually the same. So this goes here and the samplers will come here. Okay. Let's put it here itself. Okay. Now can you push the sampler further inside the network? So I mean, here if you think about it, I have two signals, x1 of t say and x2 of t. They are multiplied and then sampled. So here at the output, what we have? If I sample at x1 of nts times x2 of nts. I mean, this is it's a waste of resource, right? I'm multiplying for all time and sampling only once. So what can I do? Before the, I mean, each of these signals can be sampled first and the samples can be multiplied. Okay. So here I'll push the sampler and even here this signal is going to be sampled. Okay. So if I have to sample the signal, what should I do? I'll replace t by n times ts. What does this simplify to? 1, right? Because I mean fs and ts cancels. Here have b per j 2 pi. That's simply 1. So what can I do? I don't need multiplier. This is basically 1. I'm just multiplying the signal with 1, so I don't need a multiplier at all. Okay. So here also the same thing. I don't need the multiplier. Okay. So now we have, I mean, simplified it. I have samplers and I know I have the summation later. I'll again push it outside the summer. Okay. It's like the sampler came in, ate everything and went outside. Right? Is that fine? So now what do you see? This is the what? How does it look like? This effectively is like an LDA filter. Okay, so I can say this is some equivalent filter. And what is the frequency response? It's summation of all the harmonic transfer functions of our LPTV network. Okay. So what we find is, if I take a signal, feed it to an LPTV network, and I take the output of the LPTV network and I sample it, I can get the same samples by giving this input to an equivalent LTA filter, okay, and whose output is also sampled at the same time instance. Is that point clear? So to summarize, if you have an LPTV network pairing at fs, you give some input, say v1 of t, you get v2 of t, but instead of taking the continuous time output, you sample it and take v2 of nts. I can obtain the same samples here by passing the input to an equivalent LTA filter, which I will call H equivalent of J2 pi f, whose output is also sampled. Okay, so both of these will give this. But what can you say about, let's say this is v2 hat of t? Can you comment about these two? They need not be same, okay, because the way we derived it was, this was our output signal this portion we replaced it, and only after sampler we get the same output samples. It doesn't mean this signal is same as the output of the LPTV network. Okay, so these two guys need not be equal. Right? But as long as you sample both the signals at the same time instance, the samples will be equal. Okay? So this was something similar to what we saw with the impulse response case, right? For the inter-reciprocity. The shape of the impulse response we can't say, but if you sample the impulse response, the values will be equal. Okay? Okay, so now this is good, but what is H equivalent of F? What was this? Sum of all the harmonic transfer functions of the LPTV network. Okay. So how do you think we can find this? What is one brute force way? I mean, the equation is in front of you, right?
Find different HK.
Yeah, one brute force way is you find HK for.
We can put B equal to 0 in that, then find the total sum. Like when we will expand the whole LPTV Fourier.
Yeah, we'll come to that. Yeah, exactly. We'll come to that, right? I mean, one way is brute force is this, but this definitely looks like very inefficient, right? Because you take everything, sum it, and lose everything. So whenever you have some inefficient, stuff like this, there is always room for innovation. And as he clearly pointed out, we can actually use the properties of Fourier series and transforms. So for the LPTV network, h of t comma tau is the impulse response. I take Fourier series, what do I get? hk of tau. I take the Fourier transform of this, what do I get? The harmonic transfer function. Okay. So now what I have is summation of all the harmonic transfer functions. So if I take the inverse Fourier transform, how does it relate to the H case? It's linear operator, so it is still summation of hk of tau. Fine. Okay, so now if I take whatever inverse Fourier series or whatever, this is basically sum of all the Fourier series coefficients. If you sum up all the Fourier series coefficients of a signal, what will that imply? What is that equal to? Huh? Okay, let's x of t, if I write it as summation ck st. So it's clear, right? This is basically h of t comma 0 or 0 comma t. Huh? Remember, this is a periodic signal in time. Okay? And let us say this is that signal. Let's say this is this. Okay? And I can expand it like this, and this hk is basically this ck. So if I were to get summation of ck, what is this equal to? This is x of 0 where t is 0. Okay? Because this is a periodic signal in time, all operations are with respect to t, the time t. Okay? So what is this? H of 0 comma tau. Okay? And remember, this was the equivalent LTI's frequency response. So if I take the inverse Fourier transform, I get H equivalent of t. Right? So from both, can you, from whatever you have seen, can you tell me what H equivalent of t is? Oh, that is not possible, right? This is a function of t, this is a function of t. Okay, first of all, if I say H equivalent of t, what does it mean? When am I applying the impulse and when am I observing the response? Tell me the time instance, right? If I say h of t, an impulse response, this is just, for we apply at t equal to 0. You apply at 0, and when do you observe? At t. Okay. So this, if I say h of 0 comma tau for the LPTV, what does it mean?
Observing at 0 and applying at
Minus tau. Okay. I mean, see, remember this tau is basically variable. Okay. So if I were to write h of 0 comma tau is equal to, what should be this? I mean, this has to be tau. I mean, this is h of 0. I mean, remember t and tau are just variables. Okay. Here everything is, I am applying at minus tau and observing at 0. So that gives me the impulse response at tau. I mean, at least logically, does it make sense that if this is the signal you have, this is only a function of tau. So obviously this must be h equivalent of tau. Is that okay? So what is h equivalent of t? What should I do to get h equivalent of t? That's alright. This is basically. I mean, t and tau are just our convenience, right? They are just variables. I can as well say this tau comma t, and I will say tau is the time at which I observe the response. Okay, just a change of variable. Cool. So what we have is h equivalent of t is h of 0 comma t. Okay, is that correct? Yeah. Cool. So here the impulse response is observed at time t. Here, when is the impulse applied? And observed at 0. So if I apply an impulse at minus t and observe the response at 0, that gives me the impulse response value at this time instant t. Okay, so let's say this is some t1. This is this gives me one value. So let us say I want to get the impulse response at some other time t2. What should I do? I apply at minus t2, observe at 0. I don't want impulse response at only 2 time instant. I want for all possible values of time. So let's say it's t3, t4 and so on. What do I do? I'll have to do several experiments like this, but observe the response at t equal to 0. So now, I mean, this again looks like an awful lot of work. From what you have learnt, is there some other easy way in which this can be done? Yeah, so in reciprocity, what did we see? If we had an LPTV network, apply at Ti, observe at minus T naught, observe at T naught. For the adjoint network, I apply at minus T naught, observe at minus Ta. So if I use reciprocity, I will take the adjoint network. Okay. So let's say for this value, what is the time at which I should apply the impulse at? I should apply at 0, observe at. For the second experiment, T2. That's fine. This time is negated and put here. This time is negated and put here. That's all, right? So now, what is the thing that we should do to get this impulse response? Exactly. So you should form the adjoint network. At the output of the adjoint network, I will apply an impulse, voltage or current, depending on what you are doing. It is applied at t equal to 0. And I observe the response for all time, and that response directly gives me this equivalent LTI filter's impulse response. Is that okay? So, output of t is. That's fine. So, I mean, you can also look at it more intuitively in time domain. So let me also show that. This is the, okay. So the result we have as of now is LPTV varying at Fs. I sample the response at Fs. I can obtain the same samples by giving it to an LTI filter with an impulse response H equivalent of T, sampling it at the same frequency. So if I sample it at Fs, what are the time instants I am talking about? I mean, if this say some V of T, what will be the samples here? Yeah, I mean, like set of samples. What will be the first sample? We will be sampling at 0. Next sample is at what time? Is that okay? And I will do the I will sample the signal here also at the same time instance. Okay. So these two samples will be equal. We know that much, right? So, and we are interested in, what are we interested in finding? Impulse response of this equivalent filter. Okay. So say I give an impulse delta of t. What will I get here? H equivalent of t. Right? What will be the samples here? 0, Ts and so on. I know for a fact that I can get these samples by observing the samples here. Okay, and remember, this is just a hypothetical network. The only network we have is this guy. And since we know that these two samples are equal, I can observe the sample here, and that directly gives me the first sample is H equivalent of 0. Okay, so so this is say t equal to 0, I apply an impulse. Okay, so this is, let us say, H equivalent of t. The first sample I can get by observing the first sample of the LPTV network. Similarly, the second sample will be the impulse response value at Ts, and third sample will be 2Ts and so on. Now, but this is just giving me few samples. Now let us say I want to find the value of this, and this is H equivalent of t. Okay. Now let us say I want to find H equivalent of t at a time offset delta t. And remember that I can only sample the signal at these time instants. Delay the input. Okay, he is saying we'll delay the, how much should I delay the input by? So if I delay it, I will be applying the impulse here. So this is the sample I want. Okay, but still, erase these. I will still be sampling it at these time instants. So what should I do? Remember, I am going to sample it at t equal to 0. I want to get this sample. So when should I apply the impulse? I will advance it by delta t. Okay. So now this is, let us say, minus delta t. This will be the equivalent impulse response output here. I will sample it at t equal to 0. I get, maybe shifted it too much. Yeah, I will get the value at this guy. Is that fine? So apply delta of t, that gives me H equivalent of 0. So if I want H equivalent of delta t, what should the input be? T plus delta t. Okay, and if I want to do for all the other time instants, I will have to sweep delta t from 0 to infinity. Okay, so what does this say? For the first experiment, apply an impulse at 0. Okay, stuck. Okay. Yeah. This says I apply the impulse at 0, measure the output at 0. Second experiment says I'll apply the impulse at what time? Minus delta t and observe it at 0. And of course this is, let's say, minus delta t1, I'll apply minus delta t2 at 0. Okay. And this of course is what we saw when we used the Fourier transform properties also. And instead of doing all these experiments, the shortcut was you form the adjoint network, you apply impulse there, and you observe the response. Okay. So the deal is you have an LPTV network varying at Fs. The output is sampled at Fs. You can get the same samples by passing the same input to an equivalent LTI filter and by sampling it at the same time instance. And how do you find the impulse response of this equivalent filter? How do you find it? No, I mean, what is the experiment you will do to get it? Delta of t to what? We just saw, right? Yeah, we formed the adjoint network to find H equivalent of t. You form the adjoint network and you apply delta of t here and measure what is the output. Is that fine? And this directly gives us H equivalent of t. Okay. And you might remember that these two signals need not be equal. Only the samples are equal. Okay. So this thing is useful when we'll deal with noise, as we'll see later. Okay, so now let's actually focus on the topic that we started off after the mid-semester. Actually, what did we start off after the mid-semester? Noise, right? I mean, that was the whole deal. For understanding noise, we looked at all reciprocity, inter-reciprocity. Okay. So let's, let me start this. And let me quickly refresh what we saw for the LTI networks. So let us say you had an LTI network, and let's say it had only one resistor, say VN1, this is R1. So what is the pass spectral density of VN1? What is the units? Okay. So let's say I want to find the pass spectral density at the output. So due to this noise source, what will it be? Yeah, that's just, I'll just write SVN1 of f times mod H1 of f square. Right? That's basically the transfer function from this source to this. Right? Of course, if we have multiple resistors, this is summation k, this is all k. Fine? And we saw that if the network had only R, L and C, what was the shortcut to find the pass spectral density? 4 kT times real part of Z out of f, where Z out is the output impedance. I mean, across the terminals where you are actually interested in measuring the output. Cool. And we saw what mean square noise is, and what was it? If again it had only RLC, how can you quickly tell what is the mean square noise? 2 kT times E0 minus E infinity. What is E0 and E infinity? Yeah, initial and final energies when. Yeah, basically I have to, I mean, where should I apply? At the output port? Okay. At the output side, I'll have to inject charge of 1 coulomb, which is basically an impulse current. Okay. and we saw this also simplifies to kt times C0. Okay. So let's see what happens in LPTV network. So again, let's say this is the LPTV network, and we just say we have one resistor for the time being, and this is Vout, and I'm interested in finding the power spectral density at a frequency f. Okay. And yeah, by the way, how will you find power spectral density? In the sense, let us say you are given this network in lab and you have access to these two terminals. So in a lab environment, how will you measure the power spectral density? Sorry? Let's say you don't have spectrum analyzer. You have a power meter and some filters. What will you do?
Use a passive filter and then observe it. Very not filter.
Not. See, remember, a power spectral density just says the power in the signal around a frequency f in a 1 Hz bandwidth. So what you can do is you can pass the signal to a bandpass filter, center frequency of f with, let us say, 1 Hz bandwidth, and this is the bandpass filter, and the output you look at what is the power in the entire signal, and that gives the power spectral density. Okay, cool. So yeah, so now there are a couple of differences with LPTV network. So first is, if it were an LTI network, the power at a frequency f will be coming only due to a frequency f in Vn1. But now what all frequencies can contribute to the power at f plus k times fs? So we'll have summation of SVN1 of f plus kfs, and how does it translate down to a frequency at f? I mean, remember, the power spectral density is the input side power spectral density times the magnitude square of the transfer function. So this is magnitude square of the transfer function that governs the translation from f plus kfs to f. So what is that? Fine. So this is only due to the first resistor, say R1. Now let us say you have a million resistors. Say this is basically, say, M. This is HK for the mth resistor. We'll sum it up over all resistors. And I mean, if it's a resistor, you know the power spectral density is only 4 kTr. So you can basically simplify to 4 kT times Rm times mod H minus k of f plus kfs whole square for the mth resistor. Okay. Now another thing to observe for LPTV network is the fact that if you have the noise we consider for the resistor, it turns out it's a stationary noise. So in plain English, it means that the statistical properties of the noise doesn't vary with time. So whether I observe these statistical properties now or tomorrow or century later, it's going to be same. Okay. And with LTI networks, such a stationary random process was processed by an LTI filter. And remember, an LTI filter is just imparting different gains at different frequencies. And the gain it imparts to a particular frequency is also not changing with time. It's just some h of f. So what can you say about the noise at the output of the LTI filter? Will it be stationary or non-stationary? It will also be stationary, right? This is stationary and this is imparting a gain which is not independent of time. Sorry, which is independent of time. So the output noise is also stationary. But with LPTV network, the gain it imparts to a particular frequency, it varies with time, right? Because the frequency response, which is basically the gain at a complex exponential at a frequency f, which is h of f comma t. So it varies with time, and it not randomly varies with time, it periodically varies with time. So we have a stationary random process that is getting filtered by an LPTV network whose gain varies periodically with time. So what can you say about the output noise?
Cycles.
Yeah, that's a technical term. That statistical properties of the output will also vary periodically with time, and the technical jargon is cyclostationary. Okay, and so this is the output path spectral density, and if you have to find the mean square noise, what do you do? I mean, this is the I just integrate, right? This is just the power at around a frequency of in a 1 Hz bandwidth. The power in the entire signal is present across all frequencies. So you integrate from this guy. At least from here it looks like it is actually very difficult to do, and it turns out it is indeed difficult to do, and you resort to simulators. Okay, but interestingly, as we were discussing some time back, many times we are not interested in the output signal as a function of time. That is, we are not interested in looking at the output for all continuous values of time, but only the samples. Okay. So here I am interested in taking the samples. Say this is some V out of MTS, and looking at only the mean square value. So now let us say again this network has only one noise source for simplicity. So this noise source is processed by an LPTV network and the output is sampled. So can I get the same samples by doing something? Yeah, I will take the same noise source here, pass it to an equivalent LTI filter, say H equivalent 1 of F, and sample. Okay. Now this is good because now we have reduced this problem to dealing noise in LTI networks, which we are well versed. So if let us say this input has a path spectral density S Vn 1 of F, and let's say this is some V out hat of T. What can you say about the path spectral density at V out hat? That is basically the input side path spectral density times mod H equivalent 1 the whole square. So what is the mean square noise of V out hat of T? That's going to be integral of this. Okay, this is V out hat of T mean square, right? So what can you say about the mean square noise of these samples? I know the mean square noise for the signal. What can you say about the mean square noise of these samples? Why is it same?
There's a constant value.
What is constant value?
The integral will give some value.
Correct. Integral is giving some value for this, but when I am sampling this and taking the samples.
No, V out square T.
Right.
So that will be a fixed value, constant value.
Yeah. I mean, okay. This is a constant value. Okay, I just write it like this, right? V out of T. Say. But when I sample it, it's some other signal, right? So why do you think it is same?
When it is a stationary and the sample will be following the same kind of pattern.
Simple logic, right? I mean, now this is a stationary random process passing through an LTI filter. The output is also stationary. So it doesn't matter. The statistical properties are going to be same when you observe it at any time instant. Okay. So you take it at 0 ts, 2 ts, or at whatever time instant, the properties are going to be same. So this will be indeed equal to the mean square value of the noise samples. Well, other way to think is, so let us say this continuous time signal had a path spectral density which looked like this. Okay, so let's say shown only something. Okay. Now I am going to sample this signal. This is the power spectral density for the continuous time signal. Okay, S V out T. This is getting sampled. Now from your intuition, when you sample it in time domain, I'll have periodic repetitions in frequency domain. So let me push it here. So this is the original spectrum. When you sample it, the frequency axis is limited to 0 to fs by 2, right? Or say minus fs by 2 to plus fs by 2. So everything beyond that is going to fold back. Okay, so this portion is already there. All of these will actually fold back. So when you have to find the mean square noise, you will integrate this entire curve. That is giving some value. Now we will integrate it over minus fs by 2 to plus fs by 2, and that's basically same as integrating the entire curve. Does it make sense?
So when it will fold back,
Right.
I mean, intuitively we can say that the sample will follow the same pattern.
Yeah, here also, right? I mean, you have, let's say, the diagram might not be clear. Say you have something like this. Okay, and let us say this is minus fs by 2, fs by 2, right? So for the continuous time signal, the area under this entire graph was the mean square value. Okay, so now for the sample signal, the spectrum is spanning only from minus fs by 2 to plus fs by 2. So I'll have something here, I don't know what it is. And to find the mean square noise of the samples, I'll have to take the area of this portion. And what I'm saying is, when you sample it in time domain, at least it intuitively makes sense that you will have aliasing in the frequency domain. So this portion of the spectrum will actually come directly, and everything beyond that will also fall back here.
Actually, samples are independent of each other, so we are directly able to add the powers. Otherwise, if anything happens,
Sample doesn't mean about samples. I mean, this doesn't mean that the output samples are independent. I mean, you are assuming that this will all add up and form a white noise.
samples will be independent of each other.
Need not be, right? If you have a power spectral density,
I mean, the resistor is generating noise that is each
Yeah.
point is independent.
true, but the resistor noise is processed by a filter. The moment you pass the noise through a filter, the filter is going to add some memory, right? So it is not as if I mean, if you had to have all independent samples, the power spectral density will be white. Okay, but now you don't have a white power spectral density. So I mean, what happens is, I mean, the spectrum in the continuous time, that will all fold back, and the entire portion will actually fold back within this span. So whether you take the area of the samples, I mean, you take the power spectral density of the samples from minus fs by 2 to plus fs by 2, or take the area from minus infinity to plus infinity for the power spectral density of the continuous time signal, both of them will be exactly equal. Does it make sense?
Actually, my confusion was like if we consider a general signal, when aliasing is happening, so for in a given frequency band, it need not alias in a constructive way. Like we can't always add up the power.
Okay.
Here we are doing it.
Yeah, here see power spectral density, I mean, okay, if you go to the properties, power spectral density is basically mod of something square, it can never be negative. Power spectral density is always positive. So you'll never have a destructive case here. If you take a normal Fourier transform, yes, it is possible. But power spectral density is mod square of something. The moment you take power is positive, right? So you'll never have a case where something cancels something. Okay. Okay, so we'll stop here.